All right, ladies and gentlemen, you are about to watch Chapter 8, Unit 1 on bonding from Ralston Valley High School's AP Chemistry online lecture series. We'll be looking at an introduction to different types of bonding in this lecture. We'll discuss in greater detail ionic bonding models, and we'll finish up this lecture with a discussion of a type of calculation called a lattice energy calculation. So without any further ado, let's go ahead and get started. So up until this point of the year, we've been focused on the individual properties of atoms. But atoms themselves don't exist in isolated situations. Atoms exist in a world where they can interact with one another. And when you bring two atoms closer together, those atoms are going to interact based upon the Coulombic forces of attraction and repulsion due to their charged particles present in those atoms. And as a result, when you move atoms closer together, it changes the potential energy of the system due to the relative position of those charges. Now, in a situation where the potential energy of the system decreases as the atoms move closer together, we can find a stable arrangement that occurs when the system achieves its lowest possible potential energy state. And that stable arrangement of those atoms in a lower potential energy is what we refer to as a bond. The bond will form if the energy of the bonded molecule is lower than the energies of the atoms that exist as separated entities. And looking at the diagram that we've got here on the right-hand side, you can see that as the two atoms come closer together in terms of the internuclear distance, the potential energy of the system is decreasing to a minimum, which occurs when those two nuclei are approximately about 0.074 nanometers apart from one another. And that distance where the potential energy of the system is at its lowest is what we refer to as the bond length of that particular bond. And you'll notice that compared to completely separated atoms, who by definition have a potential energy of 0 relative to one another, when we move those hydrogen atoms close together at that bond length of 0.074 nanometers, the potential energy of the system is 458 kilojoules per mole lower than it would have been had the atoms been completely separated from one another. So that's the minimum potential energy point of the system, the distance at which the bonding occurs. And you'll also notice that as we bring those atoms closer together than the bond length, the potential energy of the system again starts to rise. And we can justify this observation by considering that not only are there attractive forces, that is, the nucleus of one atom is attracting the electron cloud of the other, that's affecting the potential energy of this system, but there also can be repulsive forces as well. That is, repulsive forces between the electron clouds of the two atoms. And additionally, when you get those atoms really close together, we see repulsive forces between the two nuclei, making the potential energy of the system increase. So again, we find the bond length at the distance where the potential energy of our system of two atoms is at a minimum. So we now recognize that bonding occurs because it lowers the overall potential energy of a system when more than one atom is involved. We're going to talk next about different modes of bonding or different models of bonding we see depending upon which types of atoms are involved in those bonds. This is review from last year, so we'll cover it fairly quickly here. The first type of bond we would expect to see is what's referred to as an ionic bond. That ionic bond is a result of the electrostatic attraction between oppositely charged cations and anions as part of a crystalline lattice. We remember from our bonding model from last year that metals generally are large atoms with large radius and therefore a weak hold on their outermost valence electrons. And nonmetals tend to be relatively smaller and more electronegative, that is, they have a better ability to attract electrons. So in an ionic bonding model, a metal loses hold of one of its outer valence electrons when that electron is picked off by the smaller, more electronegative nonmetal. And we see a transfer of the electron from the metal to the nonmetal, resulting in the formation of oppositely charged cations and anions. And the electrostatic force of Coulombic attraction holds those oppositely charged cations and anions together. So that is, again, our ionic bonding model, which is going to occur between two atoms, one of which is a metal and the other which is a nonmetal. The next type of bond we're going to be discussing here is referred to as a covalent bond. By definition, a covalent bond occurs when we see a shared electron pair between two adjacent atoms. And the mutual attraction between the nuclei of those two atoms and the shared pair of electrons between them is what holds that bond together. Generally, covalent bonds occur between two or more non-metallic elements. And to imagine why a covalent bond might form, let's think for a moment about what would happen if we were to take two fluorine atoms and try to apply an ionic bonding model. In this situation, if I wanted to form an ionic bond, I would have to remove one of the electrons from one of the fluorines and give it to the other in order to form oppositely charged cations and anions. And from an energy standpoint, that doesn't make a whole lot of sense. First off, because the electronegativity of both of those fluorines is the exact same as one another, and therefore there's no energetic benefit to transferring one electron from one fluorine to the other. In fact, it's actually probably energetically not beneficial, because when we remove the electron from one of the fluorines and try to give it to the other, we're actually moving that electron closer to a larger number of electrons than were present in the original fluorine that it already had come from. And therefore, we probably actually see an unstable configuration if we're trying to make that happen. But instead of transferring the electrons, if we do bring those two fluorine atoms close together, we can find a position where we put the electrons between the two nuclei, in which case they're attracted to both the nucleus of one atom and the other, which is therefore going to lower the overall potential energy of those electrons and make for a stable bonding configuration. So that is our covalent bonding model, again, between non-metallic elements generally. And last but not least, we have what's referred to here as a metallic bond. We define metallic bonding as occurring due to the collective attraction between the adjacent nuclei within a metallic lattice to the loosely held sea of electrons around the outside of those atoms. Remember from our discussion of periodic trends, metals on the bottom left-hand side of the periodic table, in particular, tend to have fairly large radii, and the valence shells of those metals tend to be, in general, a long ways away from the nucleus, meaning those electrons are generally fairly loosely held. And if we consider multiple metallic atoms next to one another, because those electrons in the valence shell are so far from their own nucleus, they really are not significantly more attracted to their own nucleus than they are to the adjacent atom's nucleus. That is, they're kind of more collectively held by all of the atom's nuclei around them. And again, we kind of see them washing over the surface a long ways from those nuclei, hopping from atom to atom with relatively minimal changes in potential energy. We call that, again, the sea of electrons. And that, again, is a function of the generally large radius of those metallic atoms. Not surprisingly, the atoms involved in a metallic bond are generally pure metallic elements or alloys. Again, an alloy is a homogeneous mixture of metals. Ones that come immediately to mind are things like brass or bronze. So now that we've discussed the different types of bonding that can occur between atoms, let's now think about why some of those different types of bonding might happen versus others. One of the things we want to take us back to here is a brief discussion of electronegativity and its effect on what type of bonding is going to occur. Recall from our previous discussions, we defined electronegativity as the ability of an atom to attract electrons to itself as part of a covalent bond. And the key idea we're going to talk about here is that it's really the differences in electronegativity between the atoms that determines the degree of how ionic a bond is versus how covalent a bond is. And note that I don't say whether the bond is ionic versus whether the bond is covalent, because as it turns out, the difference between ionic bonds and covalent bonds is not one or the other. It's really more of a continuum between, on the one hand, bonds which are mostly ionic in character, and the other hand, bonds which are completely covalent in character. There's not a clear distinction between those two types of bonds. On the one hand, if we consider the type of bond that would be most ionic in character, that should be the bond between the atoms which have the most dissimilar electronegativities. That is the metal with the weakest hold on its own outer valence electron, and the nonmetal which is most able to attract that electron to itself. But even in this most ionic of bonds, there's still going to be a certain attractive force that the metal is going to exert on the electron which it's giving up, because Coulomb's law is a law which describes the force of attraction between charged particles. It's an inverse square relationship, but that implies that as the electron moves further away, the attraction doesn't drop to zero until the electron is essentially infinitely distant from that nucleus. So even in the most ionic bond we can consider, there's still going to be a degree of sharing of that electron due to the attraction of the metal to its electron. So what would then the most ionic bond possible be? Well, if we think about our scale of electronegativity, recall that the most electronegative element on the whole table, that is the best atom at attracting electrons to itself, was fluorine in the upper right-hand corner there with an electronegativity of 3.98 Pauling units. And the atoms with the lowest electronegativity, that is the atoms with the weakest hold on their own electrons, were the atoms cesium and francium down in the bottom left-hand corner of the table. Cesium in particular has an electronegativity of only 0.7 Pauling units. So the cesium to fluorine bond would be the most ionic a bond could possibly be. That is, those electrons are being shared in the most unequal mode possible. Now, on the other hand of the scale, what would be the most covalent bond possible? And here, as it turns out, is a place where we can actually have a purely covalent bond. If you consider a bond between two fluorine atoms, for example, those two fluorine atoms have the exact same electronegativity as one another. And as such, the sharing of those electrons between the two fluorines is essentially perfect. There's no degree of ionic character in that particular bond. So essentially we have here a scale of, on the one hand, a purely covalent bond with zero difference in electronegativity on the one hand of the scale. And on the other end of the scale, we would have the most ionic bond possible, that is the bond with the least covalent character, where the difference in electronegativities between those two atoms of cesium and fluorine is about 3.28 Pauling units. And every other bond that exists out there is essentially somewhere between those two extremes of a perfectly covalent bond versus a mostly ionic bond. And generally, we draw the line somewhere around a difference of electronegativities of right around 1.7 Pauling units in terms of what we refer to as a bond that exhibits 50% ionic character and 50% covalent character. Now, that being said, we're not strictly going to make that as a cutoff for everything above that is an ionic bond and everything below that difference is a covalent bond. Because, again, remember, it's a continuum, and there's other things to consider as well. In particular, metals and nonmetals tend to have bonds that show other sort of ionic characteristics. That is, they do things like dissociate into ions in aqueous solutions. So in general here, what we're going to say is, when considering whether we're dealing with ionic or covalent bonding, let's go ahead and treat ionic bonds as being between metals and nonmetals, but recognize that those ionic bonds have different degrees of covalent character based upon how dissimilar or similar the electronegativities of the atoms involved are. So with that understanding now of the relationship between electronegativity and the type of bonding we see occurring between atoms now taken care of, let's go ahead and have a look at a quick example problem here. In this example, we're going to go ahead and predict the type of bonding that's likely to occur between each of the following pairs of atoms. And the first one we have there is a bond between potassium and bromine. If you have a look on your periodic table, you note that potassium is an alkali metal with an electronegativity of only 0.82 Pauling units. And then on the other hand of the other side of the table there, we've got bromine with an electronegativity of 2.96 Pauling units over there in the halogen family. And so if we do a quick calculation here, we find a difference in electronegativity between potassium and bromine of 2.14 Pauling units, We'll go ahead and plot that along our scale, remembering again that the difference in electronegativity can range between 0 in a pure covalent bond up to about 3.28 in that cesium-fluorine bond. And we see there that the potassium-bromine bond falls towards the more ionic end of the spectrum. So this potassium-bromine bond, we would generally consider this to be a mostly ionic bond with a small degree of covalent character because that potassium atom can still attract the electron which it's given up. Second example right here is a chlorine-chlorine bond. This one's easy. It doesn't even matter what the electronegativity is on this one because we recognize that this is between two of the same atom. Chlorine's electronegativity is 3.16. The difference in electronegativity between chlorine and itself is obviously 0, and therefore this is what we would refer to as a pure covalent bond over here on our scale. The next one's a kind of interesting case here. This is a bond between silicon and oxygen. This is a very important bond because this forms the backbone of most silicate minerals that we see in the world around us, things like mica or feldspar or quartz, the primary components of granite. The silicon-oxygen bond, looking at the electronegativities here, oxygen has an electronegativity of 3.44 Pauling units, whereas silicon's electronegativity is only 1.90 Pauling units. And that gives us a difference in electronegativities here of 1.54 Pauling units. We can go ahead and plot that on our scale here for the silicon-oxygen bond. And we see here that this is a bond which is more covalent in character. However, with a difference of 1.54 Pauling units in electronegativities, this is still a covalent bond which has a fairly profound ionic character. That is, the sharing of electrons between silicon and oxygen is not particularly equal here, even though this would generally be considered a covalent bond. And last but not least here, final example, the copper-zinc bond right there. There's only a difference of electronegativities between those two atoms of 0.25 Pauling units, looking at copper and zinc on your table there. However, before we go off and call this thing a covalent bond, remember, both copper and zinc are metallic elements. And therefore, this is not going to be a covalent bonding model we're dealing with, but instead, a shared sea of electrons we would see present in what we refer to as a metallic bond in this copper-zinc alloy called brass. All right, next up we're going to have a little bit more in-depth discussion of the concept of ionic bonding. One thing I want you to understand is that the behavior and the properties of ionic compounds are related to the strength of the ionic bonds present within the crystalline lattice. And the strength of those bonds is dependent upon the magnitude of the charges, that is the charges on the ions, and the sizes of those ions. So when we're considering things like maybe melting point or boiling point, we need to have an understanding about the properties of the ions involved to make some assumptions about why we see various compounds with the properties which we do. One thing that's important to remember is that ionic compounds are not simply a bond between two atoms. If you think about a salt crystal, the salt crystal is not just one single sodium ion bonded to one single chloride ion. It's a three-dimensional crystal lattice of oppositely charged sodiums and chlorines, and the electrostatic forces are what hold that entire lattice together. That is, one single central sodium ion is attracted to all of the chloride ions which surround it in that three-dimensional lattice. And that's one of the reasons why ionic compounds tend to have very high melting points, because it takes a lot of energy to break all of those omnidirectional bonds, that is, those bonds that point in all different directions within the crystal lattice. So let's have a look next at some of the properties we expect to see for ionic compounds. The traditional ionic compound I want you all to be visualizing in your heads when you're thinking about what these things are like is common table salt, NaCl, sodium chloride. And we can kind of think about why sodium chloride or other ionic compounds are the way they are based upon our understanding of the ionic bonding model. So, first property we're going to talk about here for an ionic compound is that ionic substances generally are poor conductors in the solid state. Remember, to be a conductor, there need to be moving charges present within the species. And the reason or justification we can provide that there would not be these moving charges present in an ionic compound is because within the ionic lattice, there is no translational motion of the ions themselves in solid state. If you take an ionic compound and you melt it in the molten state, those ions are now mobile, and therefore that would be a fantastic conductor of electrical current. But in solid phase, we expect ionic compounds to be poor conductors. Next property of ionic compounds. Ionic compounds generally have high melting and boiling points. If you think about it, salt dissolves really well, but dissolving is not the same thing as melting. In order to melt, you have to overcome all of the attractive forces that hold that crystalline lattice together. And remember, those ionic bonds are omnidirectional, meaning you would have to break lots and lots and lots of bonds in order to cause the ionic substance to melt. So our justification here is that strong electrostatic attraction exists between the ions, and that requires a very large amount of energy to overcome in order to cause the substance to melt or to boil. Next property of ionic compounds. Ionic compounds are generally brittle rather than malleable. If you strike an ionic compound like table salt with a hammer, that table salt is going to crack and crumble rather than bending. And as a justification here, I'd like to look a little bit more closely at the ionic lattice itself. The ionic lattice itself is held together by the oppositely charged, positively charged cations and negatively charged anions. And those are lined up such that in the normal lattice, the positives are close to other negatives and the negatives are close to other positives, which seems logical given that that would be the lowest potential energy configuration for the lattice. If we take a hammer, however, and we strike that lattice, striking the lattice is going to rearrange the ordering of the ions within the lattice. And when that occurs, you're going to end up putting positive charges next to other positive charges and negative charges next to other negative charges. And that's going to go from a low potential energy state to a very high potential energy state, causing the ionic lattice to essentially cleave itself in two, breaking apart due to the repulsive forces between those like charge particles. So our justification there again is that repulsion between the ions of like charge is going to occur when the lattice is realigned if it is struck or bent or broken. And last property here of ionic substances, ionic compounds tend to dissolve well in polar solvents. One thing I want you to be very, very aware of here is that as a justification, the AP test will not take like dissolves like as a justification for that observation. You need to talk about what really forces of attraction are taking place that cause the interaction to be favorable from a thermodynamic standpoint to cause that ionic lattice to dissolve. And really the key idea there is that if we think about a polar solvent, water being the most popular traditional one we're familiar with, there is a strong attractive force, which is what we call an ion-dipole interaction that occurs between the polar water molecules and the ions within the crystalline lattice. And if that attractive force from the ion-dipole attraction is stronger than the attractions between the ions themselves, then the formation of a homogeneous solution would be energetically favorable for that system. We'll talk about this in much greater detail when we get into your solubility unit later on in the year here, but for the time being, just recognize that it's that ion-dipole attraction that's really going to cause ionic substances to dissolve well in polar solvents like water. So as we mentioned a couple of slides ago, one of the factors which influences the behavior of ionic solids is the radius of the ions involved in forming that crystalline lattice. So we're going to go a little bit more in depth now to understanding the radius of the ions. Previously, we've had conversations about atomic radii. Now we're going to go ahead and talk about the ionic radius of a particle. Generally, when we form an anion or a cation, by either gaining or losing electrons, we're going to obviously change the size of the particle. If you form an anion, results from the addition of an electron to the species. And that additional electron is going to repel from all the other electrons within the electron cloud, which has the general net effect of increasing the radius of the particle as compared to a neutral atom. The opposite is true for a cation. When we're talking about cations, Cations have lost an electron from the electron shells around the outside, and as a result, there's less repulsion amongst those electrons, and the net effect is to decrease the size of the particle. In general, as a generalization, the smallest anion from a given period is larger than the largest of the cations. So just like for atomic radii, the factors that affect the size of the particle are both nuclear charge and the electron repulsion amongst the electron cloud. So let's go ahead now and analyze this diagram down at the bottom here, which shows the relative size of the ions formed from neutral atoms in period 2. If we look at these ions here, you'll notice that as we start off with our alkali metal in that particular period, the group 1A member sodium, sodium is the largest of the cations from the representative elements in period 2. And that sodium ion has a +1 charge. If you compare that to the next ion over, that's the magnesium ion with a +2 charge, you'll notice that that magnesium ion is significantly smaller than the sodium ion. And likewise, moving along to the +3 charge on the aluminum ion, we see again we've got an even smaller particle. And this should kind of make logical sense, because the main thing that's changing as we go across that period is an increase in the nuclear charge due to the addition of a new proton each time the atomic number goes up by 1. So if the nuclear charge increases, it would seem logical again, just like before, that the radius of the ion would decrease due to the stronger attractive force acting upon the electron cloud from the nucleus. And have a look now on the other side of the spectrum here. These other ions on the right-hand side here represent the anions. On the far right, the fluoride ion, and then moving left, we have the oxide ion and the nitride ion. And you'll notice, number one, each of those ions is significantly larger than the largest of the cations from the left side over there, which was sodium. And this, again, should make logical sense, because now we're dealing with negatively charged anions, which means each of these species have picked up electrons. And as we pick up those electrons, we see an increase in the repulsion amongst the electrons within the cloud, leading to an increase in the radius of the ions themselves. So long story short, comparing these two neutral atoms, things that form cations, the cations are smaller than the neutral ions they formed from. Things that form anions, the anions are larger than the neutral atoms which they formed from. Now, to further understand the relative sizes of the ions which we introduced on the previous slide, let's go ahead and have a deeper look at the electron configurations of those ions and use that as further justification for the observed sizes we see. In general, as a trend, ions adopt the electron configuration of the nearest noble gas. Now, that being said, that's not because ions want to have a configuration like the nearest noble gas. Ions don't want anything. There's nothing magically special about noble gases that makes all the other ions want to be like them. It's really a function of potential energy. Recall that as we gain electrons forming anions, we will gain electrons until we form a fully filled valence shell. And the addition of another electron to that anion past the fully formed valence shell would put those electrons further away from the nucleus, which is an energetically unfavorable position for the electrons to occupy. Likewise, when we're looking at the cations, we lose electrons until we've emptied that valence shell, which leaves us with the electron configuration of the previous noble gas that came before. That being said, the removal of another electron from that species would then mean we're now removing electrons from the core rather than from the valence shell, and those core electrons are much more tightly bound, being closer to the nucleus. So generally, again, we form the electron configuration of the nearest noble gas because that is the lowest potential energy configuration that the particle can achieve by either gaining or losing electrons. Now, that being said, if all of these ions are forming the electron configuration of the nearest noble gas, that means that many of these different ions are going to end up with the exact same electron configurations as one another. Those species that share the same electron configuration, we call these isoelectronic. And what I want to look at now is why those isoelectronic species are not the same size, given that they have the same electron cloud structure. And to understand that, let's go ahead and have a look at the example, which is given below here, example 2. Example 2 is asking us to give the electron configuration for the following two species. The first is neon, and the second is the aluminum ion Al3 positive. So looking at neon, neon is element number 10, and we can use our periodic table to get an electron configuration of 1s2, 2s2, 2p6. That is a full valence shell in the second energy level. That's in contrast to aluminum. Aluminum, if we look at the electron configuration for a neutral aluminum atom, would be 1s2, 2s2, 2p6, 3s2, 3p1. And we recognize then that aluminum, when it forms a cation, is going to lose those 3 electrons from its valence shell, the third energy level, which would yield an ion configuration of 1s2, 2s2, 2p6. That is to say, the neon atom and the aluminum 3 positive ion are isoelectronic of one another. That is, they have the same electron configuration. Now, given that they have the same electron configuration, we next want to think a little bit about which of these is going to be the larger or smaller ion. And if we think about it, if the electron clouds are the exact same because they're isoelectronic species, the only thing that's different between these two species then is the nuclear charge. Because the aluminum ion has a larger nuclear charge than neon, aluminum is element number 13, neon is element number 10, that implies that that larger nuclear charge in aluminum ion is going to increase the force of attraction on the electron cloud coming from that nucleus, and that's going to pull in that electron cloud more tightly, meaning the aluminum ion is going to be significantly smaller than the neutral neon atom. So this then really is our best way of understanding the relative sizes of the ions. If those ions end up as isoelectronic species, we really need to understand the difference in nuclear charge to come to an understanding of why the ion is a different size than another isoelectronic species. So last but not least, we've got an example number 3 here on this slide, which asks us to give the electron configuration for each of the following species and to order the species from smallest to largest radius. And the 4 species they're giving us here are the sulfide ion, the potassium ion, the calcium ion, and the chloride ion. And what I want you to note about each of those 4 species is that each and every one of those things is closest to the nearest noble gas, which in this case is argon. And because each of these species is therefore going to be isoelectronic with argon as they form the noble gas configuration of the nearest noble gas, that would imply, therefore, I can just simply give the electron configuration for argon, and that should be the configuration for each of these 4 species. That is, they're all isoelectronic, which means the electron configuration for all of these is 1s2, 2s2, 2p6, 3s2, 3p6. So given that they are all isoelectronic species, that means the only thing which will be changing the radius compared to one another is going to be the nuclear charge. So the species with the smallest radius should be the one with the largest nuclear charge pulling in that electron cloud most tightly, which would imply here, in this case, element number 20, calcium, would have the ion with the smallest radius of these 4. And then we would go next to potassium ion with a 1 positive charge there, which has 1 fewer proton in the nucleus and therefore a slightly less strong pull on that electron cloud. And then we would move next to the chloride ion, and then the largest of these 4 would be the sulfide ion, because again, as an isoelectronic species compared to the rest of these, the sulfide ion's nuclear charge is the smallest, and therefore it would exert the weakest attractive force on that electron cloud, leading to the formation of the largest sized ion. Now that we are armed with an understanding of the size of the different ions, cations and anions that form, we can now talk about the energy changes associated with the formation of an ionic lattice. This is an entirely new concept that we're introducing to you here, and what we're going to be talking about is calculations of what we refer to as the lattice energy. We define the lattice energy as being the change in energy that occurs as separated gas phase ions come together to form an ionic solid. Now, one thing I want you to understand here, guys, is that this is defined as a change in energy. And if we take separated gas phase ions and bring them closer together, those ions are going to attract one another, which means they're going to be forming a lower potential energy state. And as such, the change in potential energy that's occurring to those particles as they come together must be a negative value. So when we're looking at lattice energy calculations, the value of the energy change is always going to be a negative value, which implies essentially this process is an exothermic process. As it turns out, the stability of an ionic compound depends upon how strong the attractions are between all of the ions present in the lattice. And remember again that those ionic bonds that form are omnidirectional. They don't occur just between a single cation and an anion pair. They happen between a cation and all of the anions around it and vice versa. And in general, as lattice energy increases, melting points and boiling points increase as well. The more negative or exothermic that lattice energy is, the more stable that ionic compound is, the harder it is to break apart all the bonds that formed between the adjacent ions. So, to have a quick look at an example of a lattice diagram here, you see on the right-hand side there, this is a model of a salt crystal. And again, remember we were talking about how those bonds are omnidirectional. I'd like you to note here that if I just look at one single particular anion here, let's have a look at maybe that chloride ion present right in the center of that lattice. You note that it's not just bonded to one single sodium ion around it, it's actually bonded to a total of 1, 2, 3, 4, and then don't forget above and below 5 and 6 of those ions around it. Which again is telling us why those ionic compounds tend to require so much energy to cause to melt or to boil. So we'll move on the next slide to talk about how we can go about calculating lattice energy in a system. The main type of calculation involving lattice energy that we are going to be dealing with in AP Chemistry this year is what's referred to as the Born-Haber cycle. The Born-Haber cycle is essentially an application of Hess's law. You may remember Hess's law from last year's chemistry class. It was during our thermodynamics unit in which we discussed that the sum of the energy changes associated with individual steps in a chemical process must be equal to the overall energy change associated with the process we're describing. So we're going to be applying Hess's law here in a way that allows us to calculate the energy changes associated with the formation of ionic compounds from their component elements in a type of process we call a heat of formation. By definition, that heat of formation is the change in energy associated with the formation of 1 mole of a compound from the elements it's made up of in their native states. And in general, to break down the Born-Haber cycle process, there's really 4 parts that we need to be aware of. Each of these parts may be made up of multiple different steps, but in general, the 4 big overarching parts are number 1, atomization. That is, we need to take whatever species we've been given and form from those species gas phase atoms. Common ways we go about the atomization process might include taking diatomic molecules and breaking them apart, or alternately taking elements in the solid phase and causing them to undergo either sublimation to get into the gas phase or liquid phase atoms going into the gas phase via process of evaporation. So we've got atomization, that is, we form gas phase atoms first. Second, the second step is ionization. We're going to take those gas phase atoms we previously formed in the first step, and we're going to ionize them into either cations, in which case we'd be dealing with an ionization energy step by removing electrons to make those cations, or via an electron affinity step, in which we're going to form anions by adding electrons to those gas phase atoms we formed in the atomization step. Once we have ionized the species, we have now ended up with gas phase ions. We can now use a lattice energy step. And again, remember by definition, lattice energy was the change in energy associated with the formation of 1 mole of an ionic compound from its separated gas phase ions. So we'll take those gas phase ions we formed in step 2, and we'll bring them together into a crystalline lattice in step 3. And the other part of the Born-Haber cycle, which is really what makes this thing a cycle in the first place, is a heat of formation step. Again, we define heat of formation as the formation of 1 mole of a species from the elements which it's composed of in their native states. So on the next couple of slides, we're going to take a look at an example of a lattice energy calculation together. So with this example problem, we're going to go ahead and put into practice the discussion we had on the previous slide. We're going to go ahead and ask you to determine the lattice energy of the ionic compound lithium fluoride. And we've given you some processes here, stepwise processes, that are going to be used in the formation of lithium fluoride. And we're going to go ahead and ask you to both write equations which represent each of those processes, and then talk a little bit about the exothermic versus endothermic nature of each of the steps. That's going to allow us to figure out our overall heat of formation. So, to begin with, recall that the first step in the Born-Haber process was that we want to atomize each of the different species. And if we're talking about forming lithium fluoride from its elements, lithium in its native state exists as a solid, but we need not solid phase atoms, we need gas phase atoms. So the first thing we're going to look at here is the heat of sublimation for lithium. So let's go ahead and write an equation which represents the sublimation of solid lithium to form lithium gas. Now, because lithium gas is a higher energy state than lithium solid, that implies, therefore, that we would have an endothermic process occurring right here. And you'll note here that the data backs that up. The enthalpy change associated with forming 1 mole of lithium gas out of 1 mole of lithium solid is positive 155.2 kilojoules of energy per mole of lithium atoms. So our first step in the process here for atomization, we have now sublimed our lithium to get lithium gas phase atoms. To deal with fluorine now, fluorine's a little tricky because in its native state, fluorine exists as a diatomic molecular gas. But remember, we need not molecules, we need atoms. So the next step here is we're going to look at how we can make fluorine atoms in the gas phase out of fluorine molecules in the gas phase. And we're going to write this equation a little bit differently than what you've seen in the past here. Because I'm interested in the formation of 1 mole of atomic gas phase fluorine, we're going to have kind of a weird coefficient here of 1/2 F2 molecule forming 1 mole of fluorine atomic gas atoms. And essentially, to go from fluorine molecules to fluorine gas atoms, I have to break apart the bond between those two fluorine atoms in the molecular state. So that's why we call this a bond energy step. I'm essentially breaking apart that diatomic molecule to form atomic fluorine gas. And again, because I'm breaking apart a molecule, that's a process that's going to require me to do work to break that chemical bond, which means this also is an endothermic step in my cycle. And we see here again that's supported by the data. We have an enthalpy change of positive 75.3 kilojoules per mole of fluorine gas formed. All right, so we've now got our atomization part taken care of, and we're going to move on next to the ionization part of the Born-Haber process. We need to make separated lithium ions and fluoride ions out of our now gas phase lithium atoms and fluorine atoms. So the first step is we're going to go ahead and deal with lithium in terms of an ionization energy step. If I take lithium atoms in the gas phase and I remove electrons from them, I will end up with lithium ions. And essentially what I've just described right there is the energy change associated with the removal of an electron from a gas phase atom. And by definition, that is an ionization energy. Because it requires energy to remove electrons from the atoms because the nucleus is attracting that electron. That implies this also is an endothermic step. And we see again there, we've got an enthalpy change here of positive 520 kilojoules per mole of electrons removed from those lithium gas phase atoms. So we've made our lithium atoms into lithium ions. We now need to do a similar process for fluorine. But when we're forming fluoride ions, we need to form negatively charged anions now, which means we're not looking at ionization energy this time. We're now looking at that new idea we introduced to you this year earlier of electron affinity. Recall, electron affinity is the energy change associated with the addition of an electron to a gas phase atom. And so I can write my electron affinity step for fluorine by starting with fluorine gas atoms, adding my electron to them, and ending up with gas phase fluoride ions. Now, because I'm adding an electron to a fluorine atom that has a strong attraction to that electron, we see here that the electron affinity step is actually an exothermic step, which implies our enthalpy change for this process is one of the negative enthalpy changes we're going to see here. So our electron affinity has got a negative 333 kilojoules per mole of fluoride ions formed for the enthalpy change. All right, and now we come to the heart of the problem here, to our lattice energy step. This is the one we're looking for the enthalpy change, so we're not going to give you that value. But we can still write an equation that's going to help us to apply our Hess's law that will allow us to figure out what the overall lattice energy is for this process. So recall, we defined lattice energy as being the change in energy associated with the formation of 1 mole of an ionic solid from separated gas phase ions. So I can now write that process out. I'm going to start on the reactant side with the separated gas phase lithium ion and the separated gas phase fluoride ion. And on the product side, I'm going to have those ions come together and form our solid lithium fluoride. Now, again, I don't know the enthalpy change here, but I can define if this is going to be exothermic or endothermic by recognizing that if I am making those bonds in forming the ionic lattice, that's bringing oppositely charged things together, which is a process which lowers the potential energy of the system. And that must therefore be an exothermic step. So whatever this value ends up being, it's going to be a negative value for delta H for this process. And last but not least, our final step here, which is really not really a step, this is really the overall reaction we're dealing with here, is what we refer to as a heat of formation. Again, by definition, a heat of formation reaction is a reaction that ends up yielding 1 mole of the compound, and it forms it out of elements in their native states. So I'm going to write as my product here the compound I'm looking at forming here, which again was the lithium fluoride. And to make 1 mole of lithium fluoride, I need 1 mole of lithium atoms as a reactant, because 1 mole of lithium fluoride has 1 mole of lithium atoms in it. But here's the trick here. I don't need 1 mole of fluorine, because remember, fluorine in its native state is a diatomic molecule. So rather than 1 mole of F2, I really need 1/2 mole of F2 to end up yielding 1 mole of fluoride ions to use in my lithium fluoride for that product. So my reaction for the heat of formation is going to be lithium solid plus 1/2 F2 gas forms LiF, my lithium fluoride solid. And now that I've gone through and had a look at all of those steps, let's go ahead and think about how Hess's law applies. If I add each of those steps together, you'll notice that I can start canceling out a number of different things that end up on both sides of the equation. So to begin this cancellation process, you can note here that in my heat of sublimation reaction, I have lithium gas on the product side, and in my ionization energy step, I have lithium gas on the reactant side. So I can go ahead and cancel out lithium gas from both sides of that equation. You'll also notice from the bond energy step, I have fluorine gas on the product side, and I have atomic fluorine gas on the reactant side of the electron affinity step. So I can also cancel that out. And continuing along right here, you'll see from my ionization energy step, I have lithium ions on the product side in the gas phase, which I can cancel out with the lithium ion in the gas phase from the lattice energy step. And I also have that electron, which is produced in the ionization energy step, which I can cancel with the electron from the next electron affinity step that comes following. And a couple more here things to cancel out. You'll see from that electron affinity step, I end up producing fluoride ions in the gas phase. And that fluoride ion in the gas phase ends up canceling with the fluoride ion in the gas phase in the lattice energy step immediately below it. And looking at all those cancellations, the only one thing that I haven't really dealt with right now is, it looks like the lithium solid that we started with in the heat of sublimation, that hasn't canceled. 1/2 F2 gas from my bond energy step, that has not canceled. So those are the two things that are on the reactant side. And the only thing that didn't cancel out on the product side is the lithium fluoride from the lattice energy step, which means the sum of those first 5 steps of the reaction, the heat of sublimation, the bond energy, the ionization energy, the electron affinity, and the lattice energy, the sum of all of those equations yields the overall equation for the heat of formation reaction of lithium solid plus 1/2 F2 gas forms lithium fluoride solid. And to apply Hess's law then, I know that the overall energy change of my heat of formation reaction must therefore equal the sum of the individual energy changes of all of those steps. So I can now state that the energy change of 155.2 kilojoules per mole from my heat of sublimation plus my 75.3 kilojoules per mole from the bond energy step plus 520 kilojoules per mole from the ionization energy step minus the 333 kilojoules per mole from my electron affinity, plus whatever unknown value the lattice energies change is for that process, the sum of each of those values must equal negative 594.1 kilojoules per mole of lithium fluoride formed from my heat of formation step. And all that remains now is a tiny bit of simple algebra to come up with our final answer, which, solving for the lattice energy, gives me a value of negative 1011.6 kilojoules per mole of reaction. Now, that is a very large negative enthalpy change there, which again should make sense because, recall, lattice energy is the energy change associated with bringing together separated gas phase ions to form a crystalline lattice. And that large negative heat of reaction there really represents the idea that, yeah, forming a ionic lattice is an energetically favorable thing to occur. It's going to require a lot of energy to break all of those bonds apart if I wanted to undo that process. So we've calculated now a lattice energy using Hess's law and the steps of the Born-Haber cycle. So the diagram we have here is a visualization of the Born-Haber cycle for the lithium fluoride that we just had a look at in the last example problem. This diagram represents changes in energy of the system as we go through the various steps of the Born-Haber cycle. And where I'd like you to start in this diagram is right here, the point where we are at lithium solid plus 1/2 F2 gas. And we're going to take that as kind of our base level energy for this system. And walking through those steps, you see if I start with lithium solid plus 1/2 F2 gas and undergo the heat of sublimation process for subliming lithium from a solid to a gas phase atoms, you see that we go up 155.2 kilojoules per mole of lithium, which is sublimated there. And that leaves us now in a new state in which we have now lithium gas phase atoms, and again, the fluorine gas. And the next step up along that process is we're breaking the bonds between the fluorine molecules. So going from 1/2 F2 gas to just simply fluorine atomic in the gas phase requires us to supply the bond energy of 75.3 kilojoules per mole of fluorine atoms produced there. And that again increases the energy of our system. And then we get to our next big endothermic step here, in which we see an increase of 520 kilojoules per mole to go from lithium gas and fluorine gas to lithium ions in the gas phase and fluorine gas. And that's again the ionization energy step right there, which is the last of our endothermic steps. And that takes us to the highest energy point in our cycle. For our next step, we see we have a drop in energy as we go through the electron affinity step for fluorine to go from fluorine gas atoms to fluoride ions in the gas phase. And so we're dropping down in our electron affinity by negative 333 kilojoules per mole of fluoride ions produced. And then we find our big step right down here, which takes us all the way down to the bottom of our diagram, where we are at the energy of lithium fluoride in solid phase, in which we take the lithium ions in the gas phase and the fluoride ions in the gas phase, and we bring them back together to form our ionic lattice of lithium fluoride. And that exothermic change in energy we see associated with that step is the lattice energy of lithium fluoride. And that was our unknown energy change in our Born-Haber cycle. So to figure out what that unknown value actually was, we're going to swing back around to the left side of our diagram and note that the other way we could have described that process of going from lithium solid plus 1/2 F2 gas into lithium fluoride is simply via the heat of formation. That was the same overall resulting reaction that we observed, then the sum of the individual steps of the heat of sublimation, the bond energy, the ionization energy, the electron affinity, and lattice energy. Both of them took us from where we started as lithium solid and 1/2 F2 gas to what we ended up at as lithium fluoride. And that heat of formation you see there, it's negative 594.1 kilojoules per mole of lithium fluoride formed, regardless of the path we take to describe the reaction. And because of Hess's law, the sum of the sequence of steps on the Born-Haber cycle must equal the overall heat of formation for that lithium fluoride solid. So this is just a visual representation of exactly what we saw in the last problem. So for our last topic of conversation for this lecture, we're going to talk about a topic that the AP test might test you on in terms of your understanding of why some ionic compounds might have a larger, more exothermic lattice energy than others. And to start off this conversation, I'd like to take you back to an equation you've seen on a number of occasions at this point. This equation here on the left side is Coulomb's law, which relates the force of attraction between two charged particles to the magnitude of the charges, here represented by Q1 and Q2. And it also inversely relates the square of the distance separating those charges to that force of attraction. So we've seen this a number of times before. What we're going to do here is a quick manipulation of Coulomb's law. If you remember from physics days, force times distance gives us work. And work is essentially another way of talking about a change in energy of a system. So if I can kind of imagine here multiplying both sides of this equation by some distance, one of the distances in the denominator is going to cancel out, and I'm going to end up with a force times a distance, which really is an energy, in this case, the lattice energy. So as it turns out, the lattice energy is essentially can be calculated by a rearranged version of Coulomb's law's equation. And essentially the same sort of idea holds true. That is, the lattice energy is larger if the magnitude on the charges is larger. And the lattice energy is also larger if the distance separating those ions in the lattice is smaller, which should make logical sense given our understanding of the relationships between those variables in that equation. So when we're talking about what factors affect how large a lattice energy is, the primary factor we want to deal with is charge. The larger the charge on the ions, the higher the lattice energy. So that is, there's a direct relationship between those two variables. If we have +2 charge and -2 charge ions, the lattice energy of that compound in all likelihood will be greater than if we were dealing with +1 and -1 charged cations and anions respectively. The secondary factor affecting lattice energy is the radius of those ions. And earlier in this lecture, we talked to you about how you can determine the relative radius of an ion based upon its position on the periodic table. In general, the smaller the radius of those ions in the lattice, the higher the lattice energy of the particular ionic solid. So for a quick moment here, let's consider an important mineral which we mine large amounts of here on Earth. That is the mineral aluminum oxide, Al2O3. Aluminum oxide is a mineral which is the primary source of aluminum for making all sorts of products in our world. And as it turns out, the production of aluminum metal from bauxite or aluminum oxide is one of the most energy-intensive processes that we undertake as humans on our entire planet. And we can justify why that might be the case by looking at the lattice energy of aluminum oxide. If I want to separate out aluminum metal from aluminum oxide ore, I have to overcome the attractive forces between aluminum ions with a +3 charge, that is a large positive charge, and oxide ions with a -2 charge, that is, again, a large negative charge. So the magnitudes on both of the charges are very large, which means I would expect lattice energy to be great. The second thing to consider is that aluminum ion in particular, with its +3 charge, is a very, very, very small ion. Remember, the cations on the periodic table tend to have smaller radii than the native elements they're formed from. So the combination of both the large charges on those two ions and the small size of that aluminum ion means the lattice energy of aluminum oxide is incredibly large. Now, you can take a look here as another example at the bottom right-hand corner of your screen at this diagram, which shows us the lattice energy of a variety of different halide salts. This is the energy we get by combining together oppositely charged alkali metal cations and halide anions. And you'll notice there, number one, that in this case, the charges on the ions are all equivalent of +1 for the cations and -1 for the anions. So charge should have no factor at play here in terms of the lattice energies of these different compounds. So therefore, the only thing affecting the lattice energy that we're really going to be noticing is the effect on the radius of those ions. And you'll note there that the potassium ion, with larger size because of its increased number of of electron shells, the potassium ion and the iodide ion, again the largest of the anions we're showing there, has the lowest lattice energy because those ions just don't approach one another as closely in the crystalline lattice. And on the other end of the scale, we see the smallest of those two ions, that is the lithium cation and the fluoride anion, have a much larger lattice energy as they come together to form lithium fluoride than any of the other compounds which we show on the graph right there. So again, this is showing us, if we neglect the charge effect on these different systems, how the ion radius affects lattice energy for these formation of these different compounds. So last but not least for this lecture, let's do a quick check for understanding about that previous concept of comparing lattice energies. So for our example 6 in this lecture, we're going to ask you which of the following pairs of ionic compounds has the higher latticed energy. I'm going to ask you to justify your reasoning. So first one here, NaCl, sodium chloride, familiar old table salt, or the other alkali metal halide compound here, potassium chloride, often used as a salt substitute. When we look at these species, both of them have the same anion, so that's not going to have any effect whatsoever. The chloride ion with a -1 charge is present in both of the compounds. So the only real difference we're dealing with is the cations here, both of which have a +1 charge for sodium and potassium being group 1 elements. So charge here seems to play no role in our lattice energy calculation, which means fundamentally the only difference, again, must be the difference in radius of the two species. So looking between the two, we see that potassium is lower on the periodic table, meaning it's got a larger radius ion, and therefore we would expect the potassium ion to not approach the chloride ion as closely in the ionic lattice, and that would mean that it's easier to separate apart those two species, leading to a lower lattice energy for potassium chloride as compared to sodium chloride. For our second example, now we've got the cations the same. We've got lithium fluoride versus lithium chloride. So again, lithium ions have a +1 charge. Both fluoride and chloride, being halide ions, have a -1 charge. So charge again has no effect. The difference now would be the difference in size of the anions. And according to the same logic as before, the larger chloride ion, being lower on the periodic table with more shells of electrons present, will therefore approach less closely to the lithium ion, meaning it's going to be easier to separate apart those two species, and that would mean that we've got a lower lattice energy for lithium chloride, so lithium fluoride would have the higher lattice energy. The third one here is a little bit trickier. In this one, we've got two magnesium compounds, magnesium oxide and magnesium hydroxide. Magnesium is a group 2 element, an alkaline earth metal, and it has a +2 charge as an ion, therefore. So we've got magnesium ions with a +2 charge. We then have the oxide ion with a -2 charge, and the hydroxide polyatomic ion with a -1 charge. So this is a little bit trickier, but we've got two factors at play here. Number one, the oxide ion has a larger, more negative charge than the hydroxide ion, which means the magnitude of charge is greater there, which by our logic on the last slide would tell us magnesium oxide should have a larger lattice energy. The other way we could approach that is that the hydroxide ion is obviously going to be larger in radius than the oxide ion because it's got that extra hydrogen stuck on it there, which would again imply those ions are likely to not approach the magnesium ion as closely within the lattice, and therefore we would expect it to be the compound with the lower lattice energy. That is, magnesium hydroxide would be lower in lattice energy. Last example here, we've got two different iron species here. This is iron 2 hydroxide, otherwise known as ferrous hydroxide, and iron 3 hydroxide, or ferric hydroxide. So same sort of logic here. Looking at our species, the iron 2 ion has a +2 charge. The iron 3 ion has a +3 charge. So iron 3 has a larger charge, which would imply a larger lattice energy. And the other thing to take into account is that the iron 3 ion has lost 3 electrons and therefore is a smaller radius species than iron 2, meaning it could approach the hydroxide ions more closely within the crystalline lattice, increasing the force of attraction between those ions and giving iron 3 hydroxide a higher lattice energy as compared to iron 2 hydroxide. So that's it for our lecture. Thanks for listening.